Thank you, everyone. I'm Vidya Vijay, product manager at CyberOptics. At CyberOptics, we design and develop 3D high precision sensors and also inspection and meteorology for SMT and semiconductor market. Today, we are going to talk about, one of the main pillars of the smart manufacturing. We'll touch on the sensing part of it, but we'll also talk a bit about how we had to work on the other two pillars as well to help our customers. And we'll see how we can increase yield and tool uptime with monitoring relative humidity. So for wafer fabrication area, when the humidity level fluctuates, there is a host of problems that can occur. They are very sensitive to moisture in the wafer environment. And excess humidity can cause oxidation and corrosion, improper addition of photoresist, problems during bonding, and all of this accumulate to operational failure in the assembly. And as the nodes get smaller and smaller, there is more critical. It is much more critical to characterize how much there is how much relative humidity is there, and also to understand what are the contaminants. This includes all 29 nanometer fabs and below. Let us see, we are talking about clean environment. We are talking about clean room fab areas, and controlled humidity areas. But there are still sources of humidity, and let us look at that. During photoresist in mask shops, the photoresist have this, they can absorb water vapor so rapidly. Their hygroscopic nature is, it can absorb anything that comes in contact. In wafer fabrication areas where there are spinners that spray on wafer surface that can result in water vapor across the entire surface of the wafer. In photolithography, again, photoresist that can, when there is water vapor absorbed in the photoresist, there is improper addition, and that is not very helpful when the patterns you want on your wafers don't stick to them. Also, as you know, when there is water vapor in your tool, pumping them down, getting them to high vacuum can slow down, which is your cryo pump can become very, very slow. And also not just these, but there is also your protective equipment and many other sources based on the type of processes where we can find, some condensation or humidity absorbed. So it is important to monitor this. Because if we don't know where the humidity is, there are many adverse effects. We call in many of the fabs, there is nitrogen purge, which is the standard medium for purging surfaces to keep them, to clear the atmosphere from other gas or liquid contaminants. XCDA is extreme clean dry air atmosphere. So in these atmosphere, when there is humidity, there is just many issues from the characterization. The resist characterization can change. Your bakeout times can change, or the entire process can become more random and less predictable. Here you can see when there is some humidity or water vapor present in the wafer, if we further use this wafer to make ICs, there's going to be many failures. Also, when the wafers are stored in the polymer cases, it can have a haze effect, which is, as you keep storing the wafers in the clear case, you can have some light scatters, which increase over time. And this creates a time-dependent haze. And this is common not just for wafer, also in reticles. where you can see how the haze looks like on a reticle, which is quartz, a glass material. And this haze does not yield into making good wafers, and it makes the entire process very very random and less predictable. So this has been a problem for a while. It's not a new problem. We know we have to monitor the humidity. So there are many ways of monitoring the humidity and characterizing when there is when what makes the humidity increase as well. There is some handheld RH meters, which, as you know, if you want to monitor in the FOUP, you have to open the FOUP. Opening it immediately can increase the humidity. And also, you know, we want to monitor the humidity in the tool, across the tool, you know, at different places. So you will have to open up the tool. Not all the spots in the tool are easily reachable. The tools are huge. Also, there are some homegrown fixtures where you have a test wafer, you have a probe and everything connected. But the limitation is you're unable to monitor the humidity across the FOUP. You want to know how the wafer, when it sits on, you know, 3 or 6 or position 15, you know, wherever it is, you're able to monitor it from top to bottom and across the wafer, not just on one point. There are solutions like where on a wafers you have these RH recorders, but you know, we want this data to be real time, not one-time data, or we want it to be real time because we want to correlate the increase in humidity with the process that's happening. We want to know that. So there are other ways where, you know, you have the FOUP. This is the FOUP where, you know, the wafers are stocked. And there are inlet ports where nitrogen or some other inert gas is purged into to clean the FOUP of any particle or, you know, any other contaminants. And then there is an outlet port. You can have a humidity monitored at the outlet port. But what happens when we have just a single point is, then again, we want to make sure, you know, if it is a 300 millimeter wafer or 200, 150, we want to make sure you are able to monitor and know the humidity across the entire wafer. Also in the FOUP from top to bottom. Because, you know, there are issues like we could see plating uniformity. You know, the uniformity is also a big concern. So we want to make sure humidity is not the culprit that causes other failures in the process. So, you know, we heard many of these problems from our application and customer base. And then we thought, okay, we need to have a sensor where we have humidity sensors across many locations of the wafer. So we have the sensor exactly like in the wafer format. So this sensor can travel anywhere a silicon wafer will travel. We also have this in the reticle format, so it applies to reticle and mask shop tools where it can travel in any tool where a reticle will be stored or stocked, not just in the FOUP. So it is important that as it travels, it's communicating in real time. Okay, they are doing a maintenance purge and something is happening. So we are able to see the data real time, and which is very important because they need to know how much to purge and to characterize their maintenance cycle. And while we were thinking about the humidity, we had these sensing modalities separated in the wafer form, but it helps some applications where, okay, if we also know the vibration. So there is a vibration sensor and a leveling sensor in this. So if we know the vibration as it is traveling across many chambers and stations in the tool, that may help as well. So in this sensor, most of our sensors are single modality sensors, but this one is a multi-mode sensor because It can do humidity, vibration, and leveling. And we had to do this because there was a need for it. It was important for customers to know and characterize not just humidity, but also vibration. And we'll see more of that in the later slides. So as it goes, it records data and tells and it communicates wirelessly via Bluetooth. So the customer can see, okay, what is happening when they do a process change or an improvement. For example, here, so there are 5 humidity sensors as we saw. So there is like, one across the here, one in each of the levers here, and there is another one, fifth one in the center. The fifth one usually runs hotter than the other sensors because it is closer to electronics. So we had to provide some type of a correction curve for that sensor. So in this example here, we had a case where, okay, they had to actually characterize their purge procedures, what they do at maintenance cycle and what they do at the process cycle. So they had a maintenance purge. So as they started purging, you can see how the humidity dropped from 40% to 15%, very, very close, even closer to 5% here. And it started increasing as soon as they opened the door. And they opened the door to do some evaluation, and then they started the process purge. But the process purge, that procedure gave them only to around 20% relative humidity. So they stopped the purge, closed the door, and then they did the procedure and brought the humidity down as they as they established a new cycle. So, and all of this is happening. The graph is plotting as the wave, as our AMS sensor is traveling through the tools, and you can see one of the sensor is running, a bit higher, higher humidity, and we give the correction curve. That's because it's very much more closer to the electronics. And I mean, this is a good case where we can see, okay, there is so much change, and each process might have very extremely dry cases, and they might require to keep at a certain percentage, and this is helpful to characterize that. Here you can see how, and also it is important to know the leveling in both X and Y, because, for uniformities and so on. And similarly for the vibration, we can see the profiles both in X, Y, and Z. And we talked about how we need to measure humidity across the wafer, not just at one point. So that is very critical too. So, and I mean, so we had these 5 sensors and real-time measurement, because there was a need to identify, okay, where is this water vapor? Where is the humidity coming from? So that is very, very important. We can just measure the humidity, but we can be wireless, go wherever the wafer goes and give them the correlation. The correlation is super important, because then they can actually rectify and prevent the problem ahead of time. There is also, the vibration and the inclination. We have this in both wafer and reticle formats. We strive hard to keep it to the wafer size and to the semi-standards of both weight and I mean, having these sensors, we want to be able to, for the application, to use as close to how they would use a silicon wafer, because they chuck it, and these are chuckable, and they come as thin as it can be. It's not as thin as the silicon wafer itself, but we try to keep things to minimum thickness, and different products vary with thickness, but it is important to be able to go to places where a wafer or a reticle would normally go. You can see a couple of tools here. I mean, if we don't have something wireless, these are all steps towards smarter manufacturing. We need to be wireless. We want to be able to go into the big tools and understand where the problems are and help with this environmental issues like, humidity and temperature, and tell them what is happening as they go through the process. And I mean, if it is a reticle sensor, it can go through the microenvironment, it can travel through the reticle library, it can go through anywhere in the reticle stalker, and it can also sense inside a pod, reticle pod. That's where the reticles are stored. So you in a SMIF pod, so it can also measure inside a case. So basically, we go wherever the reticle and wafers go, and we want to be as close as the semi-spec for these actual reticles and wafers are. Here we had a measurement in a case. You can see how they opened the FOUP and they did a purge, but when you do a purge, you would expect the humidity to go down. But there was an issue we were able to figure out with our real-time software, and you can drop these markers wherever you can, so you know what is happening and there is a record of what is going on. There is also ways where you can compare last time you did. So you're measuring something real time, but you also want to look at when was the last time it worked well. So you can compare to see what is going on. Here you can see the purge wasn't uniform. So there are probably some liquid contaminants and particles present in the FOUP still. Similarly, we can do this similarly for vibration application, where in the vibration we can plot the X, Y, and Z. We can measure the G's, and here we can see graphs before and after tuning. For example, you could see some vibration here, and a good 88% improvement after tuning. And also, again, I mean, in the Y direction, we can see around Y direction is going up and down, and you can see still some 64% improvement. Z gives us the best improvement after tuning here, 98%. What at the end happens after tuning the robot? First of all, your vibration is reduced. Anytime vibration is reduced means the wafer or the reticle is going faster, so it's traveling less time. But it can also indicate things like, okay, it's not just the tuning. All of a sudden, you are usually okay in the process with this amount of vibration, but there is huge amounts of vibration. And then, maybe, it's the bearings or something else has gone bad. It's not just the tuning. There is probably more need before things fall apart, like preventative maintenance can be done. Sensors. Again, if the sensor can go wherever the wafer goes, then it helps to pinpoint the location. And when you see signals real time, you can say, okay, it was going from the end effector to the next chamber, and so on. You can indicate where the vibration came from as well. And in this case, it increased yield 2 to 3 wafers per hour per tool. This is huge savings. We understood, we plot the XYZ and the RMS in G's for the vibration, but it is important to give FFT curves, frequency response in the same amplitude in the frequency response. Then if there are a couple of different motors or something else involved, it can indicate, okay, it can help them identify the source better. So there is also the FFT, which is computed in the software that is provided. So we can identify the source of the vibration, not just if the vibration is present. The leveling is more like a bubble level, but extremely accurate to 0.03 degrees. And this leveling is important because you want to be not always at level. Some applications may want it to be tilted a bit, but with this you can calibrate how much of the tilt you want. Or if you need to be at perfect level, this is very, very helpful to tell you, okay, how level you are. It gives you a visual and also a plot to make sure, okay, how much is your X and Y? And if something changes, this also helps if you need to retune your robot, if it is not placing it properly in a chamber, or if something else is happening, something else is loosened. Why, this can be indication of other issues as well. If it is not leveled, the silicon can get scratched or hit something, or it can just cause particles if it is not placed level and there is a gap and so on. So we saw this need. I mean, we talked about how important it is for us to sense environmental humidity and things like that. It is so important as the nodes get smaller to know what the particles and where the particles are coming from, leveling, inclination, and vibration to help with increasing the lead and also to reduce downtime. If we can characterize vibration, it's not a binary thing for vibration. You can have some vibration and still be okay. So that it may help the sensors like AMS, which we saw, multi-sensors can help characterize and qualify, equipment and robot transfers. It can reduce maintenance cycle, because if we know, okay, this is the vibration that's expected, now it has exceeded and maybe a longer maintenance cycle has to be called in right away before you endure more expenses because of a tool crash. It also reduces resource need. Before the wireless technology, customers had to move and open up tools. Some majority of the tools run hotter. So you're waiting for the tool to go down on temperature. You're waiting for the tool to pump down to be at atmospheric temperature. We still have to cool down for our sensors to be in the tool, but at least you don't have to open up and re-clean and look for particles again and so on. All of this can happen with the tool intact. That is important. And this establishes and it helps. We want these processes to be streamlined. That is again a step towards smart manufacturing. We want to be able to automate, and in order to automate, we want that real-time signal. We want the real-time signal. Hey, something is not normal. It can be either humidity or vibration, but and so people can be we can be proactive about issues before it can happen, and that is how we can save time and money. And the tools are expensive, and we want to be able to keep them running at all times without any yield issues. For example, an issue in a mask can get carried over to wafers and the wafer lots. I mean, it could be very, very disastrous. So we talked about sensing, and then the second pillar is communicating, signal connecting. We right now communicate Bluetooth, but in future we are planning to be more Ethernet and IoT type of things, where We can connect to, we can do more smarter applications and indications to the customer. The real time, I mean, signal, because it is harder to have, we have this UI, very nicer for different applications, but we also have something called a software development kit, because it is harder to customize it for different customers. And if we tell them, we give them a library, and then they can say, okay, if the vibration exceeds so much, 0.5G, I would like the couple of engineers to let them know to go check or to call for an alarm for immediate maintenance. So all three pillars are very important, and having, we are well thinking in that way, and we want to go more Ethernet and go towards that technology. So we can talk. It is, if there are fab people listening and OEMs, it is harder with security these days to go into Ethernet right away. Bluetooth is much more easier to penetrate because of security reasons. So there are other things, not just about connectivity and being smart. Security comes into a big play. And these are the things we are thinking about right now at CyberOptics, how to be secure, how to give more intelligent feedback, and how to improve our accuracy even further. As the nodes get smaller, our need for becoming thinner is a big key. We want to be thinner and thinner, and we also want to be more accurate. The accuracy, the quality of sensing is a huge key, like Bobby mentioned in the first topic there. Quality of sensing is super important, and also the accuracy. And the challenge is, okay, we have all this technology and we have to be really thin, just like a silicon wafer. So those are the challenges we are thinking about these days. Apart from that, I would like to conclude with, we not only measure leveling, vibration, humidity, particles, gapping, we also do gap measurements. We have a teach sensor with a camera, which can, teach robots to place or align. We also have a resistance sensor for etching applications where you want uniformity. So we can measure resistance as well. Thank you so much for the opportunity. And I am opening up for questions.
Okay.